completely useless. Okay. I was just told that it's been recorded. Okay, and so then, let me start. This work is joined with my colleague from Keio University, Hideki Tanemura, and it's up on the archive, and it's still we send it to Annals of Applied Probability so it's being reviewed, refereed there for the last 8 months. Okay, so let me start, but first let me give the structure of the talk. The first part is about an introduction to some mathematical models on the evolution of species. And in the second part, we'll present our contribution. And this is a wonderful quote from Ambrose Bierce from 1874, because it's about evolution of species. So those who are horrified at Mr. Darwin's theory may comfort themselves with the assurance that if we are descended from the ape, we have not descended so far as to preclude all hope of return. It's from a very old book, actually. Okay. So the real work here started with the Bak-Sneppen model. And the Bak-Sneppen model, what it is, it's a population consisting of n species located in a circle. And each of the species has fitness parameter associated with it. So the fitness of the ith species at time 0 is fi, and these are all IID uniform random variables between 0 and 1. First, let's talk about the triviality. So evolution suppose fi of n is that you take the lowest, the species with the lowest fitness at time n. So that is the one given in the second line of this equation, and change it by an independent from an independent collection of uniform random variables. Okay, and do nothing else. But this is really, as I told you, it's a trivial model because you can easily show that fi of n goes to 1 in distribution as n goes to infinity, as both the n's go to infinity. So what we do is we add a twist to it, and that is the Bak-Sneppen model. So we have IID uniform sampling as usual, but not only at the site of the minimum fitness, but also at its two neighbors. So here, for example, if I is the one with the minimum fitness, we change for both I plus 1 and I minus 1, and keep the others intact. So here's a pictorial description. So 0.12 here is the one with the least fit. So what we do is we change the 3 of them, and now the least fit becomes 0.34. Okay. And well, I chose these numbers purposely because at the next evolution, you'll see that the 0.91, this is the most fit species, this also gets changed. Okay. So Bak and Sneppen in 1993, in a completely from simulations, observed that for large n, the one-dimensional marginals are uniform on some fc to 1, where fc is near around 2/3. In fact, they believe it's 2/3. Okay, the physicists. And also, once so assuming the existence of fc, physicists study what's called avalanches. What's an avalanche? So fix a number q between 0 and 1, and look at the first time all the species have fitness above q. That, let me call that tau 1. And then things may change, and look at the next time, tau 2, when it's again all the fitnesses are above q. Okay. So this tau 2 minus tau 1 is called the length of an avalanche of fitnesses below q. And what the physicists believe is that if q equals this magical quantity fc, then its distribution is supposed to have a power law behavior. Okay. So this is an avalanche taken from this website. So if 0.5628, if q is 0.56, then there's only 1 here, and at the next stage, these 3 change, and all 3 are less than 5.6, and then so the next stage only 0.1752 changes, etc. And it goes on until for a duration of length 11, until all of them again over 0.56. And this from here to here, where it changed, that's called the range, and the range is here 7. Okay. There's not much rigorous results about this, except this work of Mr. and Znamensky from 2003, which says that if Fn is the distribution function of the one-dimensional marginals in the stationary regime with n sites, then there exists a Q and a CQ bigger than 0, such that uniformly in n we have Fn of Q, the distribution function, is bigger than CQ. In other words, this Bak-Sneppen is indeed a non-trivial model, unlike the first trivial model which I said, where everything was converging in distribution to 1. Here it doesn't. So, although this doesn't say that there is an FC, it says that yes, there is something non-trivial happening in this model. So, and then talking about avalanches, let me first bring a triviality. Suppose n equals 3. If n equals 3, then the circle there are only 3. So all 3 of them flush at every time point, right? So if xk is the minimum at time k of all the 3 of them, and since the system is flushed at every time point, then x0, x1, etc. is an IID sequence of random variables. And so by symmetry, we know that the probability that x0 is bigger than x1, x2, xn is 1 over n. And therefore, if L is the length of an avalanche of fitness x0, probability that L is bigger than n is 1 over n. And so the expectation of L is infinity. In case n bigger than 3, strictly bigger than 3, the argument which I gave earlier fails because we do not flush the entire system at every time point. So we are getting dependence. Okay. And again, Gillette, Meister, and van der Waal showed that if L is the length of an avalanche of fitness x0, then expected L is infinity. Okay. So this lends validity to the power law belief of the physicists. But before we end this discussion on the Bak-Sneppen model, let me mention a curious result from the same paper, which says that, okay, you have your, at time 0, you have your n species with their given fitness. Suppose you add an extra few uniform random variables and call that y0, the minimum of this. And now we want to look at the avalanches of the length of the avalanches with fitness y0 or less. Okay. In that case, expectation of L is finite. Okay. So that means if I just add even one more extra uniform random variable, then this entire Bak-Sneppen model just collapses. And in the sense that the length of the avalanche is no longer a power law. Okay. So again, Ronald Meister and Anish Sarkar, they considered in 2012 considered a modified Bak-Sneppen model, which retained the signature of the original Bak-Sneppen model. What they did was, instead of replacing the least fit and its two neighbors, they considered a model where, besides the least fit, a random one is chosen uniformly from the remaining n-1. Okay. And they show that if the initial configuration has an individual of fitness 0 and the rest have fitness bigger than f, then the length of an avalanche at level f satisfies this. For f less than half, and for all n, the length of an avalanche has an exponential decay. For f bigger than half, the length of bigger than being n is a positive constant. And for f equal to half, it decays like 1 over root n in the avalanche length. Okay. And so this is about the Bak-Sneppen model. So Liggett and Schinazi, they wanted to basically they wanted to study a question which is quite topical now actually. So this Korber et al. Noted that the influenza virus is less diverse worldwide than the HIV virus is in just Amsterdam alone. However, biologically, both types of this phylogenetic tree are supposed to be produced by the same mechanism, namely mutations. So can the same mathematical model produce two trees that are so different? Okay. So what they did was they studied a continuous time birth and death model chain, with every birth having a fitness component, which is an IID random variable, and each death is of an individual which has the smallest fitness. Okay. So the birth rate of going from n to n plus 1 is lambda n, and the death rate of going from n to n minus 1 is a rate n. But remember, the death is only of the individual of the smallest fitness. So it is different from the standard birth and death chain we study or we teach in universities. So since only the ordering of the fitness is needed, because the ordering is needed just to take off the least fit. So without loss of generality, let us assume that the fitness is uniform 0-1 distributor. Okay. And let MT be the maximal fitness at time t. So what this shows that for any alpha between 0 and 1, M alpha t, that means the maximal fitness at time alpha t, being the same as mt as t goes to infinity, as for this is probability alpha is lambda is less than or equal to 1. So lambda is the birth rate, remember, and 0 if lambda is bigger than 1. Sorry, there's a typo here. What it says, therefore, that for lambda less than or equal to 1, the dominating type, the fittest type, in other words, at time t, has likely been present for a time of order t, because here we see that m alpha t is the same as mt with a positive probability, and at any given time there will not be too many types of species, and this is consistent with the observed structure of an influenza tree because it survives; it doesn't change too much. Whereas if lambda is bigger than 1, the dominating type at time t has likely been present for a time of order smaller than t, and at any given time there will be many types, and this is what's consistent with an HIV tree. Okay, so let me go to this Guiol-Machado-Schinazi model. This is 2010. So before that, let's just see that the Bak-Sneppen model suffers from two major shortcomings. The first is that the number of species is fixed, and although we study the asymptotics, as n goes to infinity, but the number of species is fixed. Also, it could be the case that along with the least fit species, we also remove the most fit because it happened to be the neighbor of the least fit species. In fact, this is the example which I gave you after the first change. The species with the maximum fitness is also changed. Okay. So this GMS proposed a model where the number of species present at any instant of time is random, and only the least fit species die. So akin to the Liggett and Schinazi model. So what they proposed was this. It's a birth and death model. So at time 0, there is a particle at time particle at 0. So 0 to 1 is the fitness scale. With probability p, there is a birth, and the individual is born with fitness f, which is a uniform random variable and independent of all other births. Okay. With the probability 1 minus p, a death takes place, and the individual with the smallest fitness is removed. Okay. So let us study. You get a simple Markov chain out of this. So if ln f is the number of individuals with fitness less than or equal to f at time n, and Rnf is the number of individuals with fitness bigger than f at time n. So remember, we are just looking at the fitness as a line between 0 and 1, and we are looking at counting the number of species, number of individuals to the left of f, which is the left ln, and more than f, which is Rn. So that the sum of this Nn is the population size at time n. And it's as I told you, it's a simple Markov chain. So starting from KL, what could happen is a new species could be born below with fitness less than f, or a new species could be born with a fitness more than f, or a death can happen, right? So this is there is a what happened? Yeah. So if with the probability 1 minus p there is a death, so this is wrong. Sorry, 1 minus p there is a death, and then LNF will become k minus 1L. So this is wrong here. With probability p times f, there will be a birth in the left side, in which case it becomes k plus 1 L here. And with probability p times 1 minus f, there could be a birth on the right side when it becomes k and L plus 1. So sorry about this. So all the minuses should be a plus and all the pluses should be minus here. So, and we can write the transition distribution also when k or L equals 0, because when k equals 0, then there can be a death from the right. But when k and L are both zeros, then nothing happens, and they have to wait. If there's a death, then nothing happens. They have to wait for a birth to happen. In this case, you can see that there's a phase transition in 1 minus p by p. Why? Because ln plus 1, if I look at just the left side, the ln plus 1 minus ln, so with probability plus 1, there is a birth here, and with probability minus 1, sorry, with probability 1 minus p, there is a birth here. With probability 1 minus p, there's a death here. And so with probability 2p and with probability 2p minus 1, ln doesn't change, but Rn can change. So what we have is that this LNF is a symmetric random walk with reflecting boundary at 0. And hence, this is a null recurrent process. So LNF is 0 infinitely open, is 1 for f less than fc, which is exactly 1 minus p by p, if you remember. And also a simple strong law of large number argument shows that if I look at an interval a to b, which is in the part fc to 1, then the number of species, number of individuals lying in this is proportional to b minus a, divided by n is p times b minus a. Okay, almost surely. This is exactly the strong law of large number result. Okay. And this is from this paper of theirs. And well, they claim that this builds on the work of Liggett and Schinazi in the sense that only the species of the least fit species is killed. They also have a continuous version of this model where new species is born at rate lambda and an existing species dies out at rate mu. So at birth, a new species has a random positive fitness determined by a distribution f, and the death is of the species with the least fitness, as before. And assuming that f admits a density, suppose at time 0 there are k species f1, f2, fk in this order, with fk equal to f, and tau k the time of survival of the species with fitness f. Then they obtain a Bessel distribution of tau k, where this ik is the modified Bessel function of the first kind with index k, which is given by this quantity. So they obtain the exact distribution function of tau k, tau fk, which is the time of survival of species with fitness f. So that what you can see is the probability that tau from that expression that if lambda f is less than mu, where lambda f is exactly lambda f is exactly lambda times the distribution function of ff at f, then probability that the time of survival is bigger than t decays exponentially in this fashion. And if lambda f is bigger than mu, then probability that this is eventual, immortality, basically, that the species with fitness f lives forever, has this probability. And also that between tau k and t, that behaves like this fashion. And if lambda f equals mu, then we have this kind of behavior. So you get a phase transition at lambda f. And then if you take, so if lambda is bigger than mu, then taking fc to be this f inverse of mu by lambda, then the species with fitness larger than fc has a positive probability of eternal survival. And as in the discrete model, the number of species with at time t with fitness less than fc is a null recurrent random walk, Bert and that chain. And also we get that similar kind of, if you have an interval a to b in the region fc to 1, then at time t, the number of species which are there is asymptotically, almost surely, the strong law of large number result, basically. Okay. So that is the original GMS model, and then it was in 2016, and our work is basically, the starting point of our work is this Benari and Schinazi model. So what they do is, so return to the discrete model. So suppose at birth, which occurs an event with probability p, remember with probability 1 minus p, there's a death, and least fit individual is taken off. But suppose at birth, with a probability r, a mutant is born with a fitness f, independent of other births. And with probability 1 minus r, the individual born has a fitness chosen uniformly at random among the fitnesses of the existing individuals. And at death, all individuals with the smallest fitness is removed. Okay. Then, just like before, we can have a similar phase transition here, where FC, the critical fitness parameter, is 1 minus P over PR. So we assume that P times R is bigger than 1 minus P here. Otherwise, this doesn't make any sense. And so they also have the same thing. So below FC, you have a null recurrent random walk. And so because you're just killing off all the sites, so it's a null recurrent random walk. And so all individuals at the site. But more importantly, what they have is that if you are given any n, k, and f, let ukn of f be the number of, at fitness s, the number of places where there are exactly k individuals. Okay. So how many sites are there bigger than f where there are exactly k individuals? Okay. So yeah, that's what I've written. A number of sites in F1 with a population of exactly k at time n. So what they do is n star here is n union 0. What they do is, if we take any Borel set from n star cross 0, 1, and you look at the empirical distribution, HNA, I'll just tell you what it is. It is this quantity, KF in A, summed over all that, UKNF, which we defined here, and UKNF plus is the same as this quantity, except it's open F. Or you can look at it as UKNG for G going down to F. Okay. So so we want to study this empirical distribution, and when there is nn of 0 is 0, then we just look delta 0, 0, whether 0, 0 is in A or not. What they showed, Benari and Schinazi, showed that Hn converges weakly to a product of a geometric and a uniform distribution. So the sites, So remember, the 0, 1 here is the location in FC, the location of where the species survives. So the sites are, of course, uniformly chosen, but the heights, or the population sizes at any of these sites has a geometric distribution with this as the parameter. Okay, so now what time is it now? 3. Okay, good. Now I'll just introduce what we are studying, and that's the preferential attachment model. And this is, well, in my institute, there's a young colleague of mine, Antur. I don't know whether he's here or not. He's the person who really taught me preferential attachment and deep preferential attachment. So all this is thanks to him that nowadays I think of this preferential attachment model. So we look at the same as the model is more or less the same as the Ben-Ari and Schinazi model. So at time 0, there's one individual of fitness 0. At time n, there is either a birth or a death of an individual from the existing population. A birth happens with probability p, a death happens with probability 1 minus p, and independent of any other random mechanism considered earlier. Okay. Again, with the same thing, in case of a birth, with probability r, a mutant is born and has a fitness parameter f, which is uniformly distributed in 0, 1. Or with probability 1 minus r, the individual born has a fitness f, with the probability proportional to the number of individuals with fitness f among the entire population present at that time. So if fitness f has a very large number of individuals already, it will attract the new species born much more than the fitnesses which have much fewer population size. So in this sense, it's a preferential attachment. It's exactly the preferential attachment model, except that we have this caveat, because if there is no individual present at the time of birth, because it can be that the entire system is flushed out, in which case the new individual is just samples fitness which is uniform between 0 and 1. And in case of death, an individual from the population at the site closest to 0 is eliminated. So this is a marked difference from the Ben-Ari and Schinazi model. The difference is that in their case, they were removing all the population, all the individuals of the least fit. So they were removing that site completely. We're not removing that site. We are just picking up one from the top and removing it. So the population size therefore just goes down by 1 there. It's not that the sites are removed. And because of this, we have a completely different Markovian structure than theirs, because our Markovian, as you will see soon, the Markovian structure we have is actually not spatially homogeneous, whereas theirs is spatially homogeneous, because once you remove the entire site, the left one just removes the total number of sites, just changes by 1, in which case it's basically the same as on the left-hand side, you're just not giving any special either preferential attachment or the uniform attachment or whatever attachment. When a species is born and is placed on the left, it just chooses arbitrarily where to go. Okay. So let me end another 10 minutes, 12 minutes with this formal structure of our model. And then in the second part, we will talk about the proofs. Okay. So let xn be ki xi, set of all ki xi, where ki's are integers bigger than or equal to 1. Small xi is as you'll see soon, is exactly the fitness site. Okay. And I going from 1 to L, where the total population at time n is divided in exactly L sites, x1, x2, xl, with the population at site xi being exactly ki. Of course, it could be that there is nothing there, in which case we take xn to be the empty set. And the process which we just described, xn is Markovian on the state space This is the state space. Empty set union the set of all possible such ki xi's coming from set gamma, which is finite. And this is the thing. So this is a Markovian model on this state space. And again, just like the GMS, original GMS model, for a given fitness F in 0, 1, let ln F denote the size of the population at time n at sites to the left of F, in other words, between 0 and F. And so formally, it is just the sum of Ks summed over all S in 0F with Ks comma S in Xn. And Rnf is the size of the population at time n that lies to the right of F, or in the interval open F to 1. And this is the formal way. And Nn is the total population at time n, which is the sum on the left plus the sum in the right. Okay. This pair ln F and Rnf is Markovian. In the sense, I just give it out fully here. So if you start from an empty, if ln F Rnf is 0, 0, then there could be an individual born with a fitness less than F, which has probability Fp. There could be an individual born with a fitness bigger than F, which is 1 minus Fp. Or there could be a death, but because it's 0, 0, it doesn't change anything. It just remains 0, 0 with probability 1 minus P. Or if ln F Rnf is 0 and Rnf is positive, then there could be a birth with fitness less than F with probability FPR. Okay. Because if there is a if it's not a mutant, if there's a birth which is not a mutant, then it has to stick to one of the existing sites, and the existing sites are all to the right of F. So the new birth in the left can only come if it is a mutant, and that has a probability F times PR. Or birth can happen to the right, and that can be either a mutant or non-mutant. So this is the probability that it's a mutant, and this is the probability that it's a non-mutant. So that this is how the right side changes. And it can be 0 Rnf minus 1. So there's a death, and because the least fit, because there's nothing on the left, so from the right of F, the death will take place, and therefore the population to the right of F decreases by 1. If there is nothing at 0 and the only things are in n, it's very similar. So there can be a birth to the left. There can be and this birth can either be a mutant or a non-mutant, or there could be one coming to the right, and that necessarily has to be a non-mutant, or there could be a death on the left. But the most interesting case, and this is the last one. So if ln F Rnf is both positive, then the left-hand side increases by 1 with the probability, well, this is FPR if a non-mutant is born, then nothing happens, or if a mutant is born. But if a mutant is born, then it chooses one of the sites to stick. The total population is NN, of which LNF is on the left side. So the probability that it increases by 1 on the left side is this quantity. And you can see that this is where the non-spatially homogeneous part comes in. Similarly, if something is born to the right, then of course this is the one where it is a mutant. So and this is the part where it is not a mutant. So it just sits on one of the sites already present in the right, and that has probability Rnf by Nn. And because we are assuming that LNF is positive, therefore there's a death from what is left there with probability 1 minus v. And it's exactly these quantities, LNF and RNF, and these quantities which make our life difficult in this model. Okay, In the earlier models, all the Markov chains were spatially homogeneous, so there wasn't really much difficulty in studying here. This is exactly what makes it more difficult. And so let me first just state some of the results, and then we'll take a break. So here also, just like earlier, because this doesn't change anything, there's a phase transition at Fc, which is 1 minus P over PR. And in this case also, just like earlier also, that if P is less than 1 minus P, that means if the death rate is more than the birth rate, then of course the population dies out infinitely often, almost surely. So these are very trivial results. Okay. In case the death rate is less than the mutant rate of RP, then the size of the population goes to infinity as n goes to infinity, and most of the population is distributed at sites in the interval Fc21, in the sense that RNFC by Nn goes to 1 as n goes to infinity, and the probability that the limits, if I take any f bigger than Fc, then probability that there is the size of the population, there's a significant population with respect to as a proportion of total population with fitness between Fc and F. That's exactly what this is saying for any F. And if in case RP is less than 1 minus P, in other words, if Fc is, well, bigger than or equal to 1, then the whole population is concentrated at sites near 1, in the sense that although the total the population is growing to infinity, but if you take any epsilon bigger than 0, and I look at 1 minus the number of the population between 1 minus epsilon to 1 with fitness, that most of it is concentrated here, practically all of it. That is the first theorem. And we also have a Glivenko type, a Cantelli type result here, in the sense that if I look at all the sites S in 0F, such that K of S is an Xn for some K bigger than or equal to 1, divided by the total number of sites where there is some population, then in the case when Fc is less than 1, this empirical distribution converges to maximum of F minus Fc and 0 by 1 minus Fc. So this really makes sense when we are looking at Fc strictly less than 1. So in this case, we have this F minus Fc over 1 minus Fc, uniformly, almost surely. Okay. And this is a very interesting result. So again, we'll look at the same kind of the question which Benari and Schinazi studied. So let UN, UK, and F denote the number of sites in F21 which has a population of exactly K at time n. Okay. And Sn is the total number of sites at time 0. No, sorry, total number of total number of sites in the entire fitness line. And UN, UK, and F plus is the number of sites in the open interval F21, or we can define it in this fashion. Okay. Then for any A in X, we can find define the empirical distribution of size and fitness in this fashion, in exactly the same fashion as we did earlier. Okay. Mm-hmm. Then what we have is that in the case when the fitness Fc is strictly less than 1, as n goes to infinity, Hn converges weakly to a product measure on n cross 0, 1. The 0, 1 part is just a uniform density in Fc21, that's given by this fraction. And the marginal on this n is pk, where pk is this quantity. Let me explain. It's 1 over p times 1 minus r. This is a beta function with a parameter, let's say f, which is exactly this quantity, and k. Okay. And well, this is the beta function, which if people here don't know about. And what does this say? I don't know whether Parthonil is here or not, but he would be happy. It says that, well, I know that for beta sk, the function behaves like k to the power minus s. And so the probability density pk is of this form. In other words, the tail is, this is correct. K bigger than or equal to j is exactly this quantity. So we have a power law behavior, a fact tail, as we say. Because remember, p times 1 plus r is bigger than 1. If you look at fc, the definition of fc, 1 minus p over pr, if it is less than 1, then you will get that p times plus 1 plus r, p times 1 plus r is bigger than 1. Therefore, this is a fraction which is less than 1. So we have a power law behavior here. Okay. And then we also study the number of individuals of a fixed fitness. So let me just tell you what we are going to do here. So if we fix a fitness f, and let n and f denote the number of individuals with fitness f at time n. When fc is less than 1, from the first theorem, we know that the left-hand side for any f, ln f I'm writing. So the left-hand side gets flushed out infinitely often, and this is true for all, for f in fc, from 0 to fc it should be. So if a mutant with fitness f is born in fc21 at some large time L, then the chances of the mutant dying is small. And so a natural question is, for some n bigger than L, how many individuals did this mutant attract by time n? In other words, what is the value of n and f? So for that, what we have is that given that a mutant with fitness f is born at time L, the number of individuals it attracts by time n, where n is bigger than L, and where both L and n go to infinity, is of this form: n by L to the power p times 1 minus r. Okay. So this is these are the main results in our paper, and it depends on a very crucial lemma here, which I'll talk about later in the next part. But I will, in the next part, what I'll do is I'll go over the proofs of the main theorems, and right at the end, I'll tell you the proof of this lemma. And this is where, as I told you, that spatially non-homogeneous part comes in, and this is where we have to be very careful. So, Yogesh, can we take a break now? Manju, can we take a break now?
Yeah, this is a good time, sure. But maybe if there are questions also, we can take.
Yeah, sure. I'm here. If you have questions.
Yeah. Okay. So otherwise, we'll meet at 3:30. We'll resume at 3:30 in 15 minutes.
Okay.
So, but if there are any questions, please unmute yourself and ask. Rahul is here.
I guess it was very simple, so there's no questions to ask.
So I myself have a request. Can you, is there, can you share this? Because I want to see the model. There were several models. I kind of lost track a little bit. So the exact model on which you are going to work.
Okay.
So it's in some slide, right? If you can share it,
I'll just go back. Yeah, so this is what I'm working on.
So this is the, okay.
The preferential attachment model. So with a probability P, there is a birth. With the probability 1 minus P, there is a death. Okay. In case of a death, the individual, only one individual from the population at the least fit site, basically, is removed, is eliminated. And if there is a birth, then the probability R, there's a completely new mutation which is happening. And this new mutation, which we call it a mutant, and this mutant has a fitness F, which is uniform in 0, 1.
So the fitness variables are in 0 to 1, the interval. Is that always?
Sorry?
The F is always in 0, 1, is it? The fitness
F is always in 0, 1. Yeah.
Okay.
Yeah. And if it's not a mutant, if an individual bond, but it's not a mutant, then it chooses one of the existing fitnesses. And what is the manner of choosing? It chooses the existing fitness, which is proportional to the size of the population at that fitness level.
Okay.
So with the probability proportional to the number of individuals with fitness F among the entire population present at that time. So, so it is a preferential attachment.
Yes.
And this preferential attachment is actually which is giving us the second theorem, this quantity, and therefore the power law behavior. In fact, I should have said this earlier. This distribution actually is quite well known. I mean, we're not with these parameters. This distribution is called the Yule process. And it was named, well, it was not named by Yule, it was named by Simon in the 1950s, but it was discovered by Yule in the 1920s. And this is what he was studying was the taxa, the total number of the species and subspecies, etc., in the British Islands. And there was a statistical study because of which he got this distribution. And then 1950s, Simon called it the Yule process. And now it is called the Yule-Simon distribution, or the Yule-Simon process. So this is an existing, I mean, I didn't know about it, but this is an existing thing.
I see. So Yule process is branching process with ages, is it? I mean, with age on
it also comes in there. It also comes in there, exactly.
Okay.
The Yule-Simon process, or whatever it's called.
I see.
In that, this is Antar here.
I can see.
Just a quick question that about Yule process and the process you have. It seems there's strongly similarity with this thing what Jim Pittman and Mark Yor worked on called the Chinese restaurant process. So your model seems to me is a generalization of Pittman-Yor Chinese restaurant process, but now with uncountably many tables, because each of your fitness is like a new table.
Oh, okay.
So and they also get this this Yule process type of limits in their solution. So there could be a link. I don't know. There could be an interesting link. Yeah.
In the preferential attachment model, always like the degree is like a Polian scheme, right? I mean, this is, I think, what I'm saying. So here, and this the generalized one is the Blackwell-McQueenan scheme is like a Polian scheme with uncountably many colors. Though I don't know whether I don't see any mapping with this, but there the limits are beta distributions.
Manju, that's a very right, exactly. But that's a kind of reinforcement where you reinforce what you only observe. What in this model you are reinforcing something else also, right? So it's not just Blackwell and McKean, but more like Chinese restaurant process.
Chinese restaurant is, I mean, a special case, right, of Blackwell-McQueen. I mean, okay.
Other way around.
The two-parameter Chinese restaurant is what you're saying.
Yeah, exactly. Right.
Yeah, so one thing to think, I mean, in that way is whether this beta distribution that is coming here is because of the result of some Polya scheme. And if you look at just one particular fitness or something like that, maybe.
Yeah. Could be. Yeah, so if you just consider everything else as a black hole and just look at one. But when I presented this talk, sorry, go ahead.
Another remark, this is kind of really coincidental. So just before coming to your talk, I was reviewing a paper.
Okay. Okay, continue, Rahul.
Okay. So where was I? Here. So I'll come back to this lemma later, but let us now prove in a random order the results which we have. So the first what we want to prove is the one where we get the Yule process. So remember Hn was, let me just recall for you. So Hn of A, so if I take any Borel set A, then Hn of A, you're looking at the number of individuals of K, a number of individuals of fitness F, and the number K in A, if it's okay, and this quantity UNF minus UNF plus divided by Sn, where Sn is the total number of sites. Okay. And we said that the Hn converges weakly to this product measure, where this part is easy to get, which is just a uniform distribution. The number of sites are uniformly distributed in FC to 1, and this pk, which comes from this Yule process. So this is what. So we want to prove this. Okay. So the first lemma we need for this is, okay, so let AKT1N be the event that a mutant born at time T1 gets K-1 attachments until time N. So the size at that fitness F, so at a random fitness F, the mutant is born at time T1, and it gets K-1 more, so the population size becomes K at time N. That this is QK of T1N. That's, we want to calculate this probability. First, we show that for the preferential attachment model, that's our model, with P equal to 1, that means no deaths. Okay. Then we have this the mean square thing, expectation of 1 over n, summation of Ti going from 1 to n, indicator of AKT1 minus Q, this probability. This square goes to 0 as n goes to infinity. This converges in mean square. And if you see this left-hand side, then you can expand it out, in which case it just becomes this quantity. So the summation over Ti is going from 1 to n, Si is going from 1 to n, because there was a square term we are looking at. So AK Si S1n intersection AKT1n minus the product of these two, because remember we're looking at the square at the variance. Okay. So this we can write out, and by conditioning this, the first part we can write out in this fashion. And then the first thing to do is to study this quantity, in the square parenthesis. And we show that for any x1, y1 in 0, 1, with x1 less than y1, if we look at this conditional probability of ak y1 n comma n given ak x1 n n minus this quantity, that this goes to 0 as n goes to infinity. And the way we do it is by breaking AKT1n. Remember, AKT1n is a mutant which comes in at time T1, and by time n, it has added K-1 many individuals to its site. Okay. So if you break it up according to the arrival times of the other K-1 mutants, then you can just play around with it, and you can get this result. Okay, so I'm not proving this, but then I'll prove the whole thing later. Okay. And this is now, once we get this, then just the nominated convergence theorem will give us this lemma. Okay. The next thing, we are still in the situation where there is no debt. Okay. So for each k bigger than or equal to 1, this sum 1 over n summation of the probabilities of ak t1n, t1 going from 1 to n, is this, which is our pk. Remember, here p equals 1. So in the expression which I had, there were some p's, but if you put p equal to 1, you will get exactly this expression there. Okay. To prove the lemma, what we first look at when k equal to 1. Okay. So that means only one individual has come. Okay. So that individual, there's this individual which is born, which has to be a mutant at time t1. And till time j minus 1, because there is no death, the total population size is j, because we remember there is at time 0, there is already one individual. Okay. And the probability that the mutant who arrived at time t1 gets an attachment at j is 1 minus r over j, because there are j individuals all over. So this is exactly q1, t1n. For k equal to 2, you can do the same calculations, because you know that there has to be one more individual coming in. It comes in at time t2. And at time t2, there are exactly t2 many individuals. And it cannot be a mutant, so that has probability 1 minus r. Therefore, we get, this is the probability that at time t2, one of these individuals, non-mutant born, gets stuck with the person who was at t1, who was born at t1. And you sum over all t2, and this is exactly the time of the second attachment. Similarly, for qk, you can do the entire sum. This is exactly what happens at qk. And by using Stirling's formula, if I look at this product, by using Stirling's formula, we get that this quantity is of the order TL over TL plus 1 to the power L minus 1, L times 1 minus R, as TL and TL plus 1 goes to infinity. And now letting n go into infinity and taking TL to be n or n times XL, if we do the calculations and can go to the limit and go and look at, because we are looking at x1 and xls, so you get this integral, and what from there you get is exactly what the pk which we want. Okay, so these are just calculations which are here in this, and these slides will, Yogesh will put it up somewhere, so you can check these. Also, it's there on the archive. Okay. So when p equals 1, the summation of this q. So what we get is this converges in probability to this quantity. And noting that Sn by n, the total number of sites, is exactly r. We call r is the density of or the probability here of a non-mutant being born. Sorry, a mutant being born. So the number of sites only increases when a mutant is born. So we get Sn by n equals r, or r almost surely, and therefore this r cancels to give us that this ratio is exactly 1 over 1 minus r times the beta function, which is pk in probability. Okay. So because I mean, we also have the other part, because the sites are uniformly distributed on 0, 1 independently, and preferential attachment does not depend on the position of sites. So we have the uniform distribution in 0 to 1 in this case, because here there is no death, so no FC. Okay. Now suppose there is a death. So consider a case when P is strictly in 0, 1. What we do is we introduce another death process, which is a pure birth process, as follows. I'll tell you why we are doing this later. At time 0, there exists one individual at a site uniformly on FC21 with probability r hat, which is PR times 1 minus FC. A mutant is born with a fitness distributed in FC21 with probability P1 minus R times 1 minus FC. So 1 minus FC is basically the length of the region FC21. And this is the probability that what's born is not a mutant. And here it was a mutant. And it's a mutant, but falling in the interval FC21. So with probability the individual born has a fitness F with a probability proportional to the number of individuals of fitness F. So the preferential attachment is still here. And we increase the corresponding population at fitness F of individuals by 1. And in a death event, nothing is happening. So with probability 1 minus P times 1 minus FC, which is the remainder of the probabilities, nothing happens. In other words, neither a birth nor a death occurs. The reason why we're doing this is because it's a priori obvious that below FC, we are getting a null recurrent process. So what is happening there is not at all of interest. For the limiting process, what happens is what's happening in FC21. So we might as well forget that part where the death happens. So what we say, nothing happens there, nothing happens. Okay. In which case, this Markov chain, so for this Markov chain, x hat n, we can define q hat k, which is the same as qk, but for this process, s hat n, the number of sites, but now only in FC21, and u hat n, which is the empirical thing which we're looking at. We can do this in the same manner as qk, sn, and un for this process, for this qk, sn, and un were done for sn, xn, but we can do the hat things for this Markov process. And then by exactly the same argument, what we will get is that this P1 minus R FC, R hat times 1 minus R hat, and the beta function. Okay. Now, sorry, this should not be R. This should be P times 1 minus FC. There's a mistake here. Now, S hat n by n is PR times 1 minus FC. Therefore, this part, this P R hat times, this again should be R hat, and 1 P times 1 minus FC gets cancelled out. Therefore, this limit becomes 1 over 1 minus R hat, this beta function, okay, which is PK. And now if we plug in the value of R hat, if we plug in the value of R hat, remember R hat is exactly this PR times 1 minus FC. If we plug in the value of R hat, and also from the main lemma, what we have is that as n goes to infinity, the total population is concentrated just on the right side, asymptotically almost surely. Okay. And so what it says is that we don't really have to look in the left side what's happening, in which case what we get from the hat process should be the same as what we got from with p equal to 1. And therefore, what we get is exactly this quantity. And this is the Yule process, which I told you about. Okay. And again, that the sites are uniformly distributed independently, and therefore the position of the sites would be uniformly distributed between FC21. And this is exactly how we get the second theorem, the theorem about the Yule process. Okay. And next we prove this theorem. So we fix an F in FC21 and L less than n, L bigger than, and L and n going to infinity. So we want to count the population size at time n at fitness F, where at fitness F, the first individual arrived at time L. Okay. And that, I told you, is like this behavior, n over L times p to the power 1 minus r. Again, since we're interested in the region F bigger than Fc, and also for the calculation of expectation, we just need to factor out the depth, because we don't need that. I mean, we don't care about what's happening at depth. So we modified the process x hat n, which where we had introduced, by removing the times when nothing happens. Remember, in x hat n, there was a certain probability that nothing happens. We just remove that. In other words, the process does not, so the process does not move then. So the way we do it is let n hat n be the number of individuals of the process x hat n at time n. We define a new Markov process, which I call x check n. So where x hat n is just x check n hat n minus 1. Okay, so n hat n is the number of individuals of the x hat process. And x hat, remember, there was no death, right? So the number of individuals at time n will be n plus 1 because there was originally one individual born at time 0. So therefore therefore n check L I'm talking about. N check L is the number of individuals of the process at time L because there is always a birth coming in. So n check L will be L plus 1 and because at time 0 there was always one individual. Okay. And so let n check Fm be the number of individuals of this process of fitness F at time m. Then this expectation, so of fitness F at time m minus 1 is this is the population. Then what is the thing? What happens here? What happens here is that with probability 1 minus p times 1 minus r, the individual which is born at time m does not come to F but goes somewhere else. If it can be a mutant or non-mutant, but it doesn't come at F. If it's a mutant, then of course it never comes at F with probability 1. If it is a non-mutant, with a certain probability it could come, but now it's decided not to. Okay. With p times 1 minus r, the mutant falls at F, and then it's because it's preferential attachment. The size of the population at F is n hat n check Fm minus 1. That divided by m, because at time m minus 1 there were exactly m individuals, and this is the remaining of the probability. And if you sum this up, then it just becomes 1 plus p 1 minus r n times this quantity. Okay. So this is if at time 0 there is an individual at fitness F, and of course this is a total population. There's an individual at time F. Therefore, we can calculate this expectation from our earlier calculations, and we get exactly this gamma relations with the gamma function. Okay. While if at time L the individual at fitness F comes for the first time at time L, then again we can do a similar calculations and we get this to be the outcome. The only thing is that at time L, there are already L plus 1 many individuals to account for. So it's exactly similar to the earlier calculation, except that in the denominator we have to, instead of m, we have to have m plus L. So, or a similar thing. So we will get exactly this thing. And then if we know that n hat n by n goes to, this is the strong law result, which is 2p minus 1. In the case n0 f equal to 1, then therefore what we get is this expectation, given that at time 0 there was an individual at f, is this quantity. And from a similar thing we get for at time L, if the individual at fitness F comes from the first time, we get this entire thing. And from this is completely useless. What we have is this expectation behaves in the same fashion as nn0 equal to 1, and from this we basically get our theorem, and just replacing these gamma things, these gamma functions, and by their approximation, and then you will get exactly the theorem which we stated earlier, that it behaves like n over L to the power p times 1 minus r. So many typos here. Okay, so now let's go back to the main lemma. And in the main lemma, remember, we have to do a bit of work because it was a spatially non-homogeneous Markov chain. So what we want to show is that for f less than fc less than 1, and for any eta in 0, 1, the probability that the total population, the proportion of the population to the left of f, remember f is less than fc, is small enough, this probability, so there exists a time t such that the total population is less than or equal to eta for all n bigger than t. This probability goes to 1. And this is, of course, the random walk result, which this part is trivial. And if f is bigger than fc, then that was the second part. We said that if I look at f bigger than fc, then in the interval fc to f, there will be a positive proportion of population. And that will be taken care of by the second part of the result. That ln of f, in other words, if f is bigger than fc, the region, the species which fall between 0 and f, they do not always get flushed out. In particular, between fc and f, there's always some remaining. So the idea of the proof is this. So suppose f is less than fc, and well, min1 we wrote, but that's there's another reason for this. The whole thing is that on the right will be much larger. The population on the right of f will be much larger than the population on the left of f. So we stochastically bound the non-spatial homogeneous chain by a spatially homogeneous Markov chain and studied a modified Markov chain. So let us have a modified Markov chain, which for any epsilon, we define ln f epsilon and Rn f epsilon as follows. Remember, the part which is 0 and other things, those are of not much interest. But if both the left and the right has at least one individual, then the way it changes is, remember, here we had ln f over nn, the total population. We just bounded by an epsilon. Here also we bounded by, I'll just go to this. The original things were, here we had LFN over NN, and here we had RFN over NN. And the death rates have nothing to do with the total population, or the population to the left or to the right. What we are doing is we are introducing a new Markov chain where instead of this LF over N, because we have an idea that the ones to the left would not contribute much. So with the quantity epsilon, I am changing it by, and ones to the right would be the major contributors. So that I'm making 1 minus epsilon. Okay. And for epsilon and 0, 1, we couple the two processes. We couple these processes, epsilon, all the epsilons. We can couple epsilon and epsilon prime, etc., such that for epsilon less than epsilon prime, the left ln f epsilon is less than or equal to ln f epsilon prime, and the ones in the right would be larger for epsilon prime bigger than epsilon. Okay, and for all n bigger than or equal to 1. So we are coupling this over all epsilons, these Markov chains. So now if I look at the ratio, the proportion of the population falling to the left of f, which is ln f by nn, then LF of n plus 1 is nothing but LF n plus 1 of this epsilon. This is the epsilon now. And the right, the part falling to the right of f has this quantity as the epsilon. Therefore, by this coupling, what we have is that ln of f, the original process, will lie between ln of 0 and ln of 1. So this is the changed process. And Rn of f will lie between Rn of 1 and Rn of 0. And because the death rate doesn't have anything to do with the fitness or anything, or the left or the right, because the deaths are just happening with probability 1 minus p, therefore the total population at time n remains unchanged. In other words, nn of epsilon, which is the sum of this, is the same as nn. And by the law of large numbers, we can get these quantity that for the epsilon Markov chain, ln of f divided by n goes to this quantity. That's just coming from the transition probabilities for the epsilon Markov chain. And from just discounting the deaths, the population at time n, surviving population at time n over n is 2p minus 1, almost surely. Okay. And remember, because 1 minus p over pr, which is the fc, is less than 1, therefore 2p minus 1 is a positive quantity. P has to be bigger than half. Okay. So for the if I call rho n f epsilon as this ratio, then from these two, we get that the strong law result would give that this rho n f epsilon as n goes to infinity converges to this quantity, which one simplification equals this. Now remember this because, well, you don't have to remember. This is the same expression which I write in the next page, but without the epsilon. Instead of epsilon, I write with x. Okay, because I want to use this h of x as my, in some sense, to bootstrap the process. Okay. So if f is less than or equal to fc, then, or it should be strictly less, sorry. Then f of p, the numerator, will be less than, if I put, instead of f, if I put fc here, then I get pr times 1 minus, this is my fc, minus 1. And the right hand side, you can just do the calculation, this equal to 0 because it's 1 minus p minus 1 plus 2. It's the 0. In other words, when x is 0, h of 0 is negative. That's exactly what I get here from this calculation. And when x is 1, then the speed over 1 minus, well, then when we compute this, you'll see that this is exactly, well, it becomes bigger than 0. Sorry. PR times, when x equal to 1, h of 1 is 1 minus this quantity. This is an equality. And PR times 1 minus f, the numerator here, because f is smaller than fc, therefore 1 minus f is bigger than 1 minus fc. And this is exactly this term here with fc. So that becomes bigger than 0. So this quantity is bigger than 0 and less than 1, because PR1 minus f is less than 2p minus 1. Therefore, this quantity, h of 1, is less than 1. So keep this in mind that h of 0 is negative and h of 1 is less than 1. Because h of 1 is less than 1, therefore, we can choose a delta, and we call this function h delta x, so that h of x plus delta is less than x. And because h is also continuous, as we saw, that function. And now we define this event, a epsilon delta, as there exists an n, a positive number, such that for all small n bigger than or equal to n, this fraction, rho n f epsilon, if you remember, was the number of individuals falling to the left of f divided by total number of individuals alive at that time. In other words, proportion of individuals, but in the new Markov chain, the epsilon Markov chain. So this is the event that for all n bigger than or equal to this capital N, this proportion is less than h delta epsilon. Okay. And from our the strong law results which we did earlier, we know that this event has probability 1 for all epsilon and delta n 0, 1. Therefore, this, going back to my eta, which was there in the definition which was there in the lemma, if I can get an epsilon c such that h delta epsilon c equals eta, and if we do the calculations, then we find that epsilon c is exactly this quantity. Okay. So we see that for all epsilon less than or equal to epsilon c, h delta epsilon eta, the maximum of this is eta. Okay. So now we do some the iteration which I was telling you about. So xn plus 1 is h delta xn. Remember, h delta x is exactly this quantity, and we noted that our choice of delta was such that this is less than x for f less than fc less than 1. Xn is decreasing, therefore the limit xn exists, and it equals this quantity which is less than 0. Okay. So now we bootstrap ourselves with this. So we take h delta kx to be h delta of this 2kx plus 1 divided by 2 to the k. And then for sufficiently large k, we'll see that there exists an NC such that h delta k1, which is defined to be h delta of k times h delta n minus 1. H delta n minus 1 is the n minus 1 composition of h delta k at 1, that this quantity is less than eta for all n bigger than or equal to NC. And from our earlier observations, we had noted about the coupling was done such that the left and the right coupled in such a fashion that for the left, for epsilon bigger than epsilon prime, the left had more with epsilon than in epsilon prime, so that the proportion would be more here. Remember, the depth doesn't have anything to do with epsilon. Okay, and also we noted that rho n s is less than or equal to rho n at the actual, for the actual process, it's less than or equal to rho n f at 1. Therefore, if I look at this intersection, which has probability 1, because each of them had probability 1, if you remember, the intersection of these events, if omega is in this intersection, there exists an n1 omega such that rho for that omega, and for the actual process, the proportion to the left is less than or equal to proportion for the new process at 1. But for that 1, we've already, by my bootstrapping, I could get it to be less than eta, which is h delta k1, which was, sorry, which we saw that it's less than eta for n bigger than nc. I'm missing. Where am I going? Yeah. Okay. So I can get. So now I can. And there exists n2 bigger than n1, so that for all n bigger than n2, again I'll bootstrap myself, and I go on bootstrapping or iterating up to nc to get that this quantity is less than h delta L to k1. And from our choice of NC, we know that this is less than eta for all n bigger than or equal to n of NC omega. And this probability is 1, as I told you earlier. So what we get is that this limit is less than equal to eta almost surely, and that's exactly our lemma. Okay, the first part of the lemma. And since I don't have much time, I won't go do the second part. So I will just end with some mean field heuristics. So let us look at the case when FC is 1 or FC is bigger than or equal to 1 in this particular case. Okay. And we are looking at the location of the leftmost site xt at time t. Okay. And yt is 1 minus xt. So the number of individuals to enter the interval xt to 1 is approximately this. So because xt to 1, this 1 minus xt is exactly this length, yt. So pr dt plus p1 minus r dt. So this is for the ones with mutation, the mutated one. These are the ones which just came and attached themselves. Yeah, so where the first term counts the births which are mutants and the second term counts the births which are not mutants. While the number of individuals being deleted from the system is approximately this quantity. This being the absolute value of the deletions, since dy dt, I have put in a minus sign because dyt yt is less than 0. Thus we have this differential equation. And if we solve this for gamma, this quantity, or which is 1 minus p minus pr over 2p minus 1, and yt comes out to be this fc minus 1 over c to the t to the gamma minus r, or it's of the order of t to the power minus gamma, as you can see from here. And the number of sites, which is RPTY. RP, remember, this is the mutant, so each mutant brings its own site. So RPTYT is of this order. Oops. So for FC bigger than 1, we also have this gamma, which was defined here, is bigger than 0, and gamma PR is a decreasing function of P. So we have these some cases here. I'll just show you. When P equals 1 minus P, then when P equals half, then gamma equals infinity. And this corresponds to the case when the process dies out repeatedly. When PR equal to 1 minus P, in other words, FC equals 1, then gamma equals 0. This corresponds to the case when there are only a bounded number of sites which are surviving. And when P equals 2 divided by 3 plus R, so it is a quantity between half and 1 over 1 plus R, then gamma equals 1, and this 2 corresponds to the case when there are only a bounded number of sites surviving. So basically what we see is that there are 3 critical values: half, 2 over 3 plus R, and 1 over R plus 1. And in these 3 critical values separate out 4 phases. So for this PC2 to 1, gamma equals minus infinity, and individuals exist in the interval FC to 1. When P lies between PC1 and PC2, gamma is in 0, 1, and the number of sites are increasing of the order of t to the power 1 minus gamma. That's what we got, remember, when we looked at RPT and gamma and YT, sorry. And the average number of individuals per site is of the order of t to the gamma, because there are these many sites, and total number is around t. So the average number is of this order. When P is between PC0 and PC1, in other words, these two, then 1 minus gamma is negative, and the number of sites is finite, with the average number of individuals being at any site being of the order of t. And when P is between 0 and PC, the process dies out infinitely off. So this is the mean field results, and I think I finished now. No, sorry, before I finish, these are the simulations which have been done by my colleague Deepa and Shortkar for P equal to 3/4, R equal to half, so that FC is 2/3. And this simulation has been conducted with N equal to 100,000. And you can see the power law behavior, if you will. There are a few points which are really above. So this is the y-axis is log base 2 of the population size. And this is the FC. So we know it's null recurrent. So there will be lots of individuals to the left. But because we are killing off the least fit, they are not distributed over the entire board part. But there are 2 new which have come in, which are just waiting to be killed here. And this is the population in log2 scales at various fitness levels. So the proportion of sites here and the population size. And this has been done by my colleague Deepa. So if he's here again, I thank him. And that's the end of my talk. And because I started with Devil's Dictionary, so let me just tell you what talk is in. I started with Ambrose Bierce. So he has a book called The Devil's Dictionary, where he has funny meanings of standard words. So he says, talk, which is a transitive verb, is to commit an indiscretion without temptation, from an impulse without purpose. So that's exactly what I did. And this is thank you, especially for my co-author, Hideki. Thanks.
Okay, so thank you, Rahul. So maybe if there are any questions.
We finished 5 minutes before, so yeah.
Yeah, there is ample time.
Right.
So I have a very simple, so I didn't understand the figures you showed at the end. So the first figure you showed at the end, what was it depicting? The previous one, Here, what is that? There is a blue almost line. It's a lot of circles, I believe, where the cursor is, right?
So this is the FC. This line, can you see the cursor?
Yeah. Oh, okay. That line is
FC. That is 2/3.
okay.
So this
but
is
what
where
do-
the population survives,
Huh.
and in this part, it's the null recurrent part.
Sorry, but what is that line of blue, horizontal line of blue there? What is it indicating? At the lowest blue, I mean blue circles.
Oh, that there is one individual here. There's another individual here. There's another individual here. And here, basically, it's a uniformly distributed. So the computer, I guess, could not pick up distinguish between the fact that it's locally finite. Therefore, it's giving a continuous line. So there are sites everywhere, basically, it's saying. But remember, it can't be everywhere. But if I look at one particular thing, so if I look at this thing, suppose it corresponds to 0.8. Okay. So at 0.8, because between 0.79 and 0.81, there were many. So this 0.8 also became blue here. But 0.8 is exactly the population size is 2 to the power d, 2 to the power 8. Okay. And similarly, if this was 0.9, this is 2 to the power whatever.
I see.
So this is the simulation, but because it's really packed here, so you're getting this full line here.
Then what is the next line? I mean, the next
line?
blue line, horizontal blue line. What is that?
So also, so let's say 0.79. Okay, 0.79 had only one individual. 0.78 could have had two. Well, this is 2 to the power 2. 4. This is not 2 to the power 2. Yeah, maybe 2 individuals. 0.78 could have 2 individuals.
Oh,
0.77 could have 8 individuals, or 2 to the 12, 4, etc. But because they're really dense, not in the mathematical sense, but they are really. Therefore, these lines become continuous in depiction. But if you come here, when you see that, let's say here, 2 to the power 6, where are the sites where there are more than 2 to the power 6? It corresponds to this blue dot here, and then some blue dots here, etc. And these blue dots. So above the line, if you see the circles, they correspond to one particular site on the x-axis, and it's telling me that there are 2 to the power so many individuals at that site.
So you could have drawn vertical lines where at each x, and that ends at the topmost circle above that fitness level. Is that right? I mean, that's the number of people. Okay, I got it. Yeah, thanks.
Yeah, but it would be so dense you would not be able to. Well, I don't know. Deepan did it for me, but I thought this was. But this is much more explicit here.
Okay. Okay, sure. Any questions, others? Okay, if not, maybe everyone can unmute themselves first. Please unmute yourself so that. Yeah, so let's thank Rahul for these 2 lectures.
Thank you.